My name is Shweta Jain. I'm a postdoc at the University of Utah. Um, my research is about bringing ideas from theory to design algorithms that will work well in practice. Specifically, I work on graph algorithms, and I work in this area called parameterized algorithms. So essentially, a lot of the computational problems that we encounter in day-to-day life are actually NP hard, and yet we encounter them every day. Something as simple as routing requires us to solve traveling salesmen. So given that these problems are NP hard, what can we do? Is there something fine-grained we can say about which problem can be solved efficiently on which instances? And so one way this is done is by recognizing certain parameters about the graph instance that we have at hand and using those parameters to design algorithms and reason that these algorithms will work fast on these instances. So we specifically took one problem that was actually inspired by biology. Assume that we are given a graph of a gene network in which we have information about the correlation of pairs of genes acting together. And we want to use this information. So use this information to find groups of genes that act together. So the way we model this problem is as an undirected weighted graph in which the edges have weight, which correspond to the correlations. And we want to discover modules, or what we call as weighted cliques in this graph, such that for every edge, the weight of the cliques that edge is a part of, those weights exactly sum up to the edge's weight. And so given such a graph, we want to find such cliques, and we're given some number k, and we want to know if we can decompose this graph into at most k cliques, k weighted cliques. And we solve this problem using a technique called kernelization. What it basically does is we give reduction rules that help us to shrink the graph so we were able to reduce the size of the graph exponentially. And as a result, the downstream algorithm was able to solve that instance in an exponentially lesser time. And that's the work that we've done so far. And our next step is going to be to consider noise in this network and see what we can do in the presence of noise.